So this is a brief discussion on Chemical Ideas 15.7, yields and atom economy. So first of all, a couple of definitions. Our actual yield, or sometimes just called yield, that's a measure of the amount of the substance actually formed, so the mass of our product formed in a reaction. Our theoretical yield is the mass of the reactant, mass of the product we'd expect to form if our reaction was 100% efficient, so no side reactions and no loss of reactants or products when we are actually carrying out the reaction. And then percentage yield is a calculation of the efficiency of the reaction, so how good we were in the real world actually producing what we'd expect. So let's start with a nice simple reaction. We've got calcium oxide being produced here just by burning the calcium in oxygen, and any time we see an equation, the very first thing we should be doing is writing relative masses underneath. So calcium there is a relative mass of 40, and then half an oxygen molecule. Here we just need one of them, so that's 16, and then the relative mass of the product, the 56, for the calcium oxide. So because it's a 1-to-1 ratio, calcium becoming calcium oxide, we'd expect 40 grams of calcium to produce 56 grams of calcium oxide, so that becomes our theoretical yield. So let's say we do the reaction, we weigh out the calcium oxide and we end up with only 50 grams of that. We can see how efficient we are just by calculating the percentage yield. So 50 grams is what we actually produced, 56 grams is what we expected, multiply it by 100 and we end up with an 89% percentage yield. So a relatively efficient reaction. Now let's say we want to look at the atom economy, which is, instead of looking at the masses you happen to be using in this reaction, now we want to look at a theoretical measure of how efficient this is as a reaction overall. We use this definition, the atom economy. So a measure of the percentage of the mass of the reactants in the final product. So atom economy is the relative mass of the useful products divided by the relative mass of the reactants multiplied by 100%. So in this example it's very easy to see without even doing calculations, as we've only got one product. The relative mass of our useful products must be all of it. Okay, so in this case our atom economy is simply 56 divided by the mass of the reactants, which in this case is 40 and 16, which is 56 also, times 100%, and that gives us obviously 100% as we'd expect. Now if we take this same synthesis, we want to make a similar product, calcium oxide, but we do it in a slightly different way this time. We see what effect that has on the yield and the atom economy. So this time, instead of starting with calcium, we're going to start with calcium carbonate. So again, first thing we do is write the relative masses underneath. So 100 grams of calcium carbonate thermally decomposed would give us 56 grams of calcium oxide and 44 grams of carbon dioxide. Now we've got our useful product, but we've also got this waste product or byproduct, carbon dioxide, something that we don't particularly need. So our theoretical yield in this case, if we start with 100 grams of calcium carbonate, we'd still get a theoretical yield of 56 grams. Let's say our actual yield this time was 52. So it's a slightly better reaction. We managed to thermally decompose most of that. Our percentage yield this time would be 52 divided by 56 times 100, which would equal 93%. But this time, if we look at the atom economy, just by looking at our reaction, we can see that it can't be as good in terms of atom economy, because we've got two products this time. If we're only interested in one of them, if our useful product this time, if our useful product is the calcium oxide, so that one's useful, so this is useful, we want this one. But if this is waste, if that's waste, then clearly some of the atoms in our starting material, our calcium carbonate, are being wasted. They're not ending up in something useful. So we do want this, but this is waste. So our atom economy reaction allows us to get a measure of that. So our useful products this time, the mass of that is the 56. That's from this equation here. and then the mass of our reactants in this case is obviously just 100 there. Multiply that by 100, and don't need a calculator to work that one out. We get a 56% atom economy. So in terms of digging the calcium carbonate out of the ground, only about half of it ends up in useful products, the rest ends up as waste carbon dioxide. So in terms of atom economy, not a great reaction, very poor on the atom economy, but in terms of overall chemical synthesis, this one's much easier because we can just dig our calcium carbonate straight out of the ground. So we can take this and use it as a way of calculating masses and percentage yields and the like for any reaction. So here we have something you'll come across in year 13. This is synthesis of aspirin from salicylic acid. So here our salicylic acid is reacted with this ethanolyting agent, ethanoic anhydride, and that produces our ethanoic acid as a waste or byproduct, and here we've got our aspirin, which is obviously a very useful painkiller. In this case actually this won't be a byproduct. This ethanoic acid can be used, can be sold, so this would be a co-product, so we would have to decide or look at the question if the exam question asks us what the atom economy is, see whether it is saying that both of them are useful or it's just one of them is useful. So let's work that one through. If the question were to ask what's the atom economy of this reaction, assuming only the aspirin is a useful product, we would use exactly the same equation, so the relative mass of useful products, atom economy in this case, if this is our only useful product, our useful products have a mass of 180, and then the relative mass of the reactants, that would be both of these two together, so 138 plus 102 times 100%, put that into our calculator, and we get 75%. So not bad in terms of atom economy. 3/4 of the reactant atoms end up in their useful final product, but still 25% wastage if we can't sell this on to something else. So if we do some yield calculations on this, let's make it a slightly more realistic reaction. So let's say that we started with 120 grams of, let's just call this X for convenience now, so 120 grams of X. What would the theoretical yield be? And let's say that we had an actual yield of, let's call this 1Y, actual yield of 92 grams. So what would our theoretical yield of Y be, and what would our percentage yield of Y be? Okay, so looking at the mole ratios here, we've got 1 mole of X forming 1 mole of Y, but we've got different masses here. So first things first, we need to work out how many moles of X we've actually got. So using our normal formula of number of moles is mass over relative mass, we can work out the number of moles of X in 120 grams. So our mass is 120 grams, our relative mass is 138 grams. Put that into a calculator, and that gives us 0.87 moles of X. And then if we look at our mole ratio, we've got 1 mole of this forming 1 mole of this, so therefore that tells us straight away that we've got 0.87 moles of Y. And then if we want to work out the mass of Y that we'd expect to get, then we're just going to do our mass is number of moles times by relative mass equals 0.87 times by our relative mass of Y, 180, and that should give us 156 grams. So that would be our theoretical yield of Y, same as the number of moles we'd expect. So if we took 120 grams of X and reacted it and everything went well as expected, we get 156 grams of Y. Our percentage yield then is just as before. We've got an actual yield of 92 and we expect to get 156. Multiply that by 100 and we would then get a percentage yield of 59%. Okay, so not a very efficient reaction here. Okay, so running through that one more time, we've got a 1-to-1 mole ratio here. 1 mole of this forms 1 mole of this, and we've got our relative masses already given. If we only have 120 grams of X, we need to work out how many moles of that is, so we use our mass divided by relative mass formula. This gives us 0.87 moles of X. Then return to the formula, one of them forms one of them, so we get 0.87 moles of Y as well, and then move our equation around, rearrange our equation to give us the mass of expected Y, so 156 grams. Our percentage yield then is the actual yield, which we're given in the question, divided by our expected yield, or our theoretical yield, times 100%, and that gives us 59%. Okay, so this is Chemical Ideas 15.7. Go back through those notes to help you, rewatch this video, and then work your way through the questions.